All right, so a key style of question in our vector calculus is ensuring that our particles collide as opposed to intersect. So don't forget the position vectors tell us the path of the particle, and so they may cross, but for them to collide, they've got to be at the same point at the same time. Okay, and so to do that, we want to equate the corresponding I and J or K components, and then solve for t, and then that t value needs to satisfy both equations for them to be at the same point at the same time. So for example, if we equate here, we get t cubed minus 9t plus 8 is equal to 2 minus t squared, which is the I components. From the j components, I get t squared equal to 3t minus 2. Now we've got two equations there. Clearly equation 2 is the one that's going to be simpler to solve because it's just a quadratic. So if I do that, I'll end up with t minus 2, t minus 1. So I get t is equal to 2 or 1. Okay, so they'll be at the same j component or j position at 2 seconds and 1 second. But will they be at the corresponding I component? If I substitute t equal to 1 into the first equation, I'll end up with 0 is equal to 1. So no, they're not going to be at the same point. But if I put t equal to 2 into the first equation, I'll get negative 2 is equal to negative 2, which is true. So it's only at t equal to 2 seconds will they collide. All right. Prove that A and B collide while traveling at the same speed, but at right angles to each other. So they collide at t equal to 2. So let's work out the speed or the velocity vector for each one. R dot of A, if we differentiate, 3t squared minus 9 plus 2tj, negative 2ti plus 3j. At t equal to 2, there's my two velocity vectors. Okay, so what does that mean? The magnitude or the speed of each of those velocity vectors both turn out to be 5, so root 25. Just using a bit of Pythagoras there, magnitude of each. But they've got to be at right angles to each other, which means the dot product should be 0. And if we work out the corresponding dot product, we in fact do get 0. So same size, same magnitude of speed, but at acting at right angles to each other. Let's have a look at another one here. So the position of a particle we give us by the velocity of the particle. So we want to find the velocity, so we're going to differentiate each. So 2 minus 2t, 2t minus 3 plus 2k. The speed of the particle is going to be the magnitude of all that. Okay, so we're going to take the square root and then square the I, j, and k components. So if we do all that and group our terms together, we end up with that expression there. The minimum speed, so we want to find out where the velocity or dv dt is equal to 0, so the acceleration is 0. So if I differentiate that expression, I'm going to end up with, obviously, that's all to the power of a half out the front, stay the same inside to the power of minus a half, then multiply by the derivative of the inside, which is 16t minus 20, which gives me 16t minus 20 over the square root of. Okay, so that's only going to equal to 0 when the top is equal to 0. So in other words, when 4t minus 5 is equal to 0, so at t equal to 5 on 4 seconds, that's where we have a maximum minimum. Okay, by rights, I probably should check to see if it is a minimum speed. If I put that into my velocity vector, the 5 on 4, and if I've worked that out properly, which hopefully I have, we'll end up with a 3 on root 2, which is just our 3 root 2 on 2 units. Okay. Example 13, similar, except we've got a little bit of trick involved here. Velocity, so again, we'll differentiate dot. So derivative of cos minus sine, so negative 4 sine 2t. Derivative of sine is positive, so it's positive 2 cos 2t, so there's my velocity. We want to know the speed, so we want to get the magnitude of that. So there's my squared and added, and then we're going to find a maximum minimum. So instead of going into a heap of calculus, sine squared is 1 minus cos squared. And if I substitute that into that, I then end up with a velocity equation in terms of cosine only. And I know the maximum and minimum values of cosine. The key one, -1, 0, or 1. So since we've got cos squared, the minimum value will be 0, the maximum value will be 1. So the maximum will occur when that 12 cos squared 2t is equal to 0, so we'll get root 20. The minimum will occur when cos squared is equal to, yeah, that's right, when cos squared is equal to 1, and we get 20 minus 12, which is root 8. All right. So look, you can go through a calculus path, but I'm a bit of a fan of if we're working with trig and the terms group together nicely, we can often do it by observation or inspection. Okay, so let's keep working through. We've got the position particle given by, where I is a J unit, projectile is fired from a point on the ground, find the time taken to reach the ground again. So obviously there's our position. So to reach the ground, it means my vertical component is 0, isn't it? So the vertical component in this case, the J component, I need 500t minus 5t squared equal to 0. Factorise, solve, t equal to 0. We start from the ground, and 100 seconds later we end up on the ground. All right. The speed at which the projectile hits the ground. So we need a speed equation, so r dot of t. So if I differentiate that, I get 400i plus 500 minus 10t. At t equal to 100, I get the vector 400i minus 500j. Now the speed is the magnitude of that, so 400 squared plus 500 squared square rooted. If we simplify, square root of 10,000 times square root of 41, so it's 100 root 41 meters per second. All right, so that's the magnitude of our speed, or the magnitude of our velocity. Maximum height of the particle, so the vertical component of the velocity will be 0, so we're heading upwards, and then so when that vertical component is 0, which is the 500 minus 10t, at the 50-second mark, that's when it's going to start falling back down again. So at t equal to 50, what is the vertical height? 550 minus 5 times 50 squared is 12.5 kilometers, or whatever, 12,500 meters. All right. Finally, the initial speed of the projectile, initial speed, so velocity at t equal to 0, which happens to be 400i plus 500j, which is not surprising given, the speed, the time it takes to go up and the time it comes back down, etc., etc. The speeds will be the same. So the initial speed is 100 root 41. Yeah. So what about 15? Suppose that the position vector of point is given by blah, blah, blah. Find the velocity and acceleration. So the velocity r dot of t. So we're going to differentiate. So we get our, derivative of cos is negative sine. So just make sure we differentiate as opposed to integrating. We'll then differentiate r dot of t with r double dot. The k value of 2 comes out the front, so we'll end up with a negative 16 cos 1 plus 2t I, negative 16 sine. So we've got velocity and acceleration, hence show that the acceleration vector is parallel to the position vector. So if we can work with our acceleration vector and take out a negative 4, that leaves me with 4 cos 1 plus 2t, 4 sine 1 plus 2t, which is the same as my position vector. So in actual fact, my acceleration is negative 4 times the position. So they're in fact parallel, isn't it? Because one's a factor of the other. 16, a little bit messy, 16, same sort of thing. We've got our r double dot of t, so we've got our acceleration vector given as, we've got initial velocity of 3 and a position of 2. Find the velocity and displacement at any time. So obviously our velocity, r dot of t, is the antiderivative of our acceleration. So carefully anti-differentiating, add 1 to the power and divide by 2. Antiderivative of sine is negative cos. Antiderivative of negative 2 is negative 2t plus c. So at t equal to 0, I get a negative j plus c is equal to 3i. So c is equal to 3i plus j. Pop that in. So there's my 3i, and there's my plus j. Okay, and now we're going to integrate again to get my position vector. So r of t is given by, and this time at t equal to 0, the position was equal to 2j. So we're just going to get d is equal to 2j, which we're going to include down in here. There's that constant of 2j in there. The speed is the magnitude of all that, which I guess in this instance, look, you could argue you could probably leave it there. There's nothing nice about that magnitude. Doesn't group particularly well. Whether that factorizes, look, it quite possibly does, but I don't know whether it changes the question a real lot. No, it probably doesn't factorize, in fact. No. 3, 3. No. Anyway, so there's our question done. Final little application is the distance travelled along a curve. So it's the curve length almost, okay? So we've done something similar in integration with methods, the length of the curve. So it's the same sort of thing. So it's the derivative of each parameter with respect to t, squared and then square root. So obviously if we come in here, the square root of the derivative of 3t minus 2 is 3. The derivative of 4t plus 3 is 4. If we square both of them, it's take square root, we end up with 5. So the antiderivative of 5 dt is 5t. Between 3 and 1 will give me 10 units. All right, so away we go.